Functions of several variables. You don't have to write this down. Just a quick review that we learned about functions before in different classes. Now we have a function of two variables, which means we'll have x and y or more inside as an input. This is a rule. A function is a rule that assigns to each ordered pair of real numbers in a set D, which is domain. D is domain. Again, don't have to write this down. A unique real number, f of x, y, or just z, so z equals, or anything else, g or whatever. That is a range. X and y are independent variables, z is dependent variables. But again, you can always increase the dimension, and now you have more things inside. You have xyz, xyz-tm, xyz-g, and so on. So it's R3, third dimension, R4, and so on. I have very good notes from my friend and colleague, Dr. Payam, so I put a link here. But it's also in my modules. I use his notes a lot. I combine his notes, ASU notes, with my own notes. So each lecture you see was like hours of preparation. At some point, that's what I mean, that I don't waste your time. When you come here, it's supposed to be a good lecture, or I feel like it's not fair to you. But in general, a quick idea that was always a function is explained as a machine. It's like a cute machine. You drop something inside, it does something. A function is a rule. It's a machine. It does something in it and spits out the answer. So we used to have x and the output was y. Well, now it's x and y and output is z. Or maybe x, y, z and output is g, and so on. So idea is still the same. It does something, spits out. Whatever it takes in is input or domain. Whatever it takes gives you out. That's output or range. In general, people get a bit confused with domain and the range, so I'd like to show it this way. There's a table in front of you. Whatever is on the floor on towards me, that's domain towards, say, y-axis. To the right, that's domain towards x-axis. So how much width it is. This is a domain, not more, not less. This is a domain. All allowable inputs are here. Where can I put my pen? Here, 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 but not over here. So everywhere here. That's domain for width. Now domain for length. Same here. So domain is where you're allowed to use inputs. That's simple as that. If there's a hole for a socket on the table, then we're gonna cut it out of the domain. I cannot put my pencil there, it will fall. Does that make sense? So that's how intuitively you can do it. And the height is also a domain, right? How high it is, and so on. Sometimes it's explained. You should draw this. It's very cute. It's like a little ghost, right? This is cool idea that domain, sometimes we see it as a projection on some kind of plane. And from this projection, we will see how the 3D or 4D or 5D object looks like. So this is the idea. F of x, y, which is, for example, equals to z, is output. Domain of two variable function will be, so I take some kind of point, how this point was created. No, not necessarily here, any point. How this point was created from some inputs on a domain, x, comma, y. This is the point. Input shoots up, creates the output. All of them created this cute ghost. Bless you. So, f of x, y, 2x squared plus y, 2x e to the yz, and so on. You can have lots of inputs. Why not? I always mention that the more you get into applications of math, the more variables there are, gravitational forces, temperature, viscosity, lots of things, and all of those will be variables, and they will be interacting with each other, and so on. So let's practice your homework. I'm definitely going to show you some homework so you don't feel upset. Your homework is pretty long, but it's only one chapter. But it has lots of problems because they're these kind of tiny problems. Homework. Let f of x and y equals 2x squared plus 3xy plus y squared. Basically, we need to teach you how to use the function notations again, just like we did in pre-calculus class. So, f of 1 and 2. I'm just going to do 1. F of 1 and 2. The other one, you can do it by yourself. What do you think we should do with 1 and 2? What? Plug it in. Plug it in. So where do I plug 1? and 2 into y. Agree or not? So that's the idea. Thank you. Good job. So we're going to plug. So now you just need to be careful. Every time you see x, wow, everyone is sneezing. Like, that's like, okay, it's a season, I understand. So everywhere you see x, you just tell your mind 1, 1, 1, and you plug 1 everywhere you see x, 1, and so on. Everywhere you see y, plus 3. Everywhere you see y, you plug 2. So times 2 plus 2 squared. So your brain have to get used to many variables now. Especially when we will be differentiating and integrating, it will be so fun. Your brain will have to assume some of those are constants while some of those are variable and then switch the order. It's going to be so fun for the brain. It's going to be like a puzzle with the puzzle. Amazing. Well, the students really love it, this chapter, because it's kind of, the idea is straightforward, but your brain struggles at the beginning until it gets it. Oh, several dimensions. That's what it means. All agree with this, plugging in? So usually if you sign them, it makes it better, easier to understand. Applications, multivariable functions are useful in real life a lot. Since life itself depends on several variables, some small examples, f of t and p, t is temperature, p is pressure, f of r and p, r is the position, p is momentum in quantum mechanics. Famous functions, it's the cost of 2 goods sold, and alpha is greater than 0 is a constant. This is called a Gope-Douglas production function, useful in economics, and so on. Graphs. Similar functions, several variables have graphs. The only difference is that in 1 dimension, graphs are curves, but in 2 dimensions, graphs are surfaces. So let's write down from curves, we go to surfaces. In 2D, so lines, curves, cubic functions, parabolas, into surfaces in 3D. The blanket, that's like the ghost thing was probably a blanket, basically. A chip is a 3-dimensional object, and so on, surfaces. So it's kind of the same idea here, nothing new, but you don't have to write it down. I think I'm giving you those notes anyways. The domain of a function f is a set of numbers x and y for which f of x, y is defined. Same with range, is a set of all possible outputs, values of z. So outputs, let me see, inputs, only allowed inputs and outputs. Nothing new, that's the thing. We're just reviewing calculus 1, and that's actually pre-calculus, into calculus 3. Now, this is interesting. Can we learn how to sketch the graph? Let's do this example. F of x, y equals square root 9 minus x squared minus y squared. We've seen this object before, and you will have to get used to it slowly. We skipped to chapter 10.6, and actually today I will mention it. Remember, you did it for extra credit. I put it as extra credit in the grade book. While you were taking exams, my multitasking skills are phenomenal. Everyone who knows me know it. While you were taking exams, I posted like 5 homeworks and quizzes grades, made like 5 emails, checked that you're not cheating, answered questions, found a typo on the exam, and so on. So 10.6 was an extra credit chapter, but it shows the classical shapes in 3D. So this is one of them. Solution. How to know what the shape is looking like. So this left-hand side is z, right? First, I will write down, okay, z. You don't have to write down z equals, but it takes less space. F of x, y is a professional way, but it takes a long time to write. And type. 9 minus x squared minus y squared. The first thing I noticed that it is positive. Mistake? And 0. Yeah, positive and 0. So it starts from 0 and goes up. Z is your 3rd-dimensional height, right? So it grows up. Let's square both sides. And now, so we remember it was positive, because now when you square it, you lose this property. Come on. Don't do that. Number 1 in innovation. Yes, thank you. Z squared equals 9 minus x squared minus y squared. Now, what do you think I should write down to completely know what the shape is? People at the back, are you okay? Yeah, okay. What do you think I should write down to know how what this shape is? Some classical way to do it. Rearrange, how? Can you tell me?
Put the x and y on the left side and put 9 as 3 squared.
Yes, let's do that. X squared plus y squared plus z squared equals to 9. Exactly. Can you recognize this? Let me put it in the green box. Look at that. Look at that. What is that? It's a sphere. We think it's complete ball, but it's not. So why? Be careful with that. We think it's a complete sphere, but it's not. Good point. It's still a sphere though, but my point is not this. So I will write down sphere, centered at 0, 0, 0. What's the radius? Radius r equals 3. You had this question in exam 1 just with less variables. But this is wrong. There's one little thing which is important. It's not a complete sphere. It is half of the sphere because of this important point. The moment they put a square root here, they cut off the negative part of the sphere. Sphere is defined as 2 halves. Upper shell, like you mentioned, shell, and a lower shell, right? So they only want one, the positive of 1. So that's why I put this note. We need to keep this in mind right away. Then when we square both sides, we're losing this property. But we need to remember that z cannot be negative. So let's add 4 letters. Hemisphere. Hemisphere means half of the sphere. Hemisphere. Lower half or not lower half. Upper half or lower half. So basically, see, it's like a drop of water if you think about it. Especially in blue color, it looks like a drop of water. You can sketch the graph quickly. Circle, and then make it 3D. And it goes up to 3 units, left to 3 units, right to 3 units, and so on. So whatever is on the floor, this shade, basically. Or what do I see when I look from the top? I see a circle, radius 3. That is domain. Domain takes x and y's as an input. Output creates this surface. So now, as a 3-dimensional creature, you see this drop of water. But an ant that's on the ground does not see a drop. The ant sees only the circle. That's what it means to be in higher dimension. So range is our outputs. So that's the shape of the z equals square root of 9 minus x squared minus y squared. Let's actually write this down. I think it's a good thing to write it down. Actually, this is your homework, so you can tell me. Some people from the back, can you tell me what I just said? I actually already said everything. Range is z belongs to what? What is the range interval? People from the back, do you know? Range. How would you describe to an ant that this is a 3-dimensional object? It has height. From where to where is my allowable height? 0 to 3. Agree? Including or not? Including. Starting from the floor and ending up to at a very, very higher spot, 3. That's an interval called closed interval. Now, people from the middle of the class. Domain. And let's call it x, comma, y. That's my domain. What's the name of the domain? Do we know the shape name? It's a circle, exactly. It's a circle centered, let me write down. Centered at 0, 0, r, still 3. So we inputting a circle, outputting a surface. Isn't cool? That's the idea. In 1 dimension, a domain is an interval. But in 2 dimension, a domain is a 2D region. So in 1 dimension, what did we have before? This was a domain from 0 to 3. And then output was like a half of the parabola, for example. Input was, in 1 dimension, an interval. like from 0 to 3. Output was a curve. Now the curve or 2D region is the input and output is a surface. So now if you go to higher dimension, the input will be a surface and the output will be a fourth-dimensional object which human brains cannot comprehend, unfortunately, but I will show you some today and you will understand them. So that's going to be pretty cool. This is the note here. You don't have to write this down, but it is pretty cool to understand. In one dimension, we inputting intervals. But in 2 dimensions, we inputting 2D regions, so increasing the dimension. The range is in fact an interval, just like in 1 dimension in here. Limits. This is your homework. You can do that. I told you, you can start this homework without me. Find the limits. We can do lots of things with functions, just like we did before, and we will do all those things. We're gonna do implicit differentiation again. We're gonna be doing logarithmic differentiation. Chain rule will happen again, but in 3 dimensions, in upper dimensions, actually. We're gonna find maximum and minimum. We're gonna find lots of optimization problems are coming again. Basically, calculus 1 in 3D. That's why I would like to have calculus 1 and calculus 3 one by one. And now you have like a whole semester gap. Nobody remembers anything. While I was talking, did anyone solve this? What is the numerator? 10 or 11? Let's check. X, sometimes you can take a pencil and do like this. X goes to what? 1, right? So X goes to 1. Limit as X comma Y goes to 1 comma 2. That means X goes to 1. So set it equal to 1. Y goes to 2. Now you carefully plug that. So if you have colors, that will help you at the very beginning, so your brain gets used to it. Color coding is fun. So it's 2 plus what? Plus 8. And the denominator 1 plus 4, which is 10 over 5, which is 2. Agree? So that is your homework. The explanation is explanation actually is more interesting than the whole, the problem. The explanation is this, check it out. So my input is X and Y, which means I have X and Y, and the output is Z, right? So this is the idea. When X and Y gets close to the 1, 2, so there's a point 1, 2 in 2D. Let me find it. 1 towards me, 2 to the right. This is the point 1, 2. We're not saying that function is there. Remember, limit is approaching, but not necessarily actually achieving that limit. So when X gets closer to 1, and let me use another color, green. When X gets closer to 1, and when Y gets closer to 2, there is a 3D shape, say a curtain. That's called a surface, classical example of surface. On that surface, Z approaches 2. On that surface, there is a point 2. So it's all happening in 3D on the surface. So it's kind of like this. With different limits, when X and Y are moving, the output on the surface approaches 2. That's the pretty cool idea. Of course, we're going to be defining continuity the same way as before. Using this idea, we can define f as being continuous. Intuitively means that the graph of f has no jumps, like we did before. No holes, no jumps. Just like I mentioned, the table should have no holes for the socket. It should be continuous. You don't have to draw this. But the idea is, I have actually really good animation about this later. But the idea is continuity, more or less the same we had in 2D. Geometric interpretation of limit of functions of 2 variables and continuity is here. Now we're talking about the surface. The surface should have no holes, no gaps, no jumps. But now it has a 2D domain, 3D range, and so on. Those planes are basically slices of the 3D surface and have very good animation on that to show you. So it's going to be better. Now, level curves, right down this topic, that's going to be important. Unfortunately, students get confused with level curves quite a lot. So I will try to explain you. We will be working on them for a while. They also go to final exam usually. Let's take it to the next level and talk about level curves. Oh, that's a pun, I guess. which is a useful tool for graphing functions in 3D and 4D and so on, higher dimensions also. Consider the function f of x with the following graph. Write down this nice bell shape. It jumped again. I still think it's a ghost though. I don't know, right? Looks like a ghost. But okay, it's a bell shape. It's nice to see it as a mountain. Then it's actually easier to understand level curves. So write down, draw this nice bell shape and make it look like 3D. So it's a standing bell. Level curves, they work like this. So let me choose another color. Let's say pink. When z equals 5, I'm fixing the height. You learned this from the first exam. What does it mean to fix some variable? Now the height is fixed and we're only looking what is happening on that shape at the level 5. So now I cannot go higher and lower. What I see is this circle. See? I see this circle on the level 5. And I can draw how long this circle is. On the right, I'm drawing it in red, in pink. This is how big the circle is when z is 5. Okay, I'm gonna go to purple. When z is 10, the circle is getting smaller or bigger? When I get higher, the z is height, now 10. Smaller, right? So I see that it's shrinking. This 3D object is shrinking with the higher I go. I still see the circle, so I'm gonna draw a smaller circle. Green. The z equals 15 seems to be the last possible point. That is my restriction on the range. I cannot go higher than 15. The circle became just a point at the very top of the bell. Where is the biggest circle? So the smallest circle is at the level 15, it's just a dot. The circle with radius 0, it's a dot. Where's the biggest circle? 0. Z equals 0. Give me this huge circle on the floor. In blue, I will draw it around everything. That is z equals 0. That's a definition of level curves. Well, it's not definition. That's a nice visualization of level curves. At each level, we have a different slice or curve. Now it looks like circle inside of the circle inside of the circle, but it gives you information. The higher you go, the more object shrinks to the radius 0. So it's collection of circles at every level. There's some circle here, and so on. But the higher you go, the smaller they become. So you look at the top. Actually, this is how you look at the screen from the top of the green point, and then it expands, and it gives you some kind of understanding what the shape is. It's expanding, right? So in 3D, that's a bell, but this is how it looks if you look at the bell from the top. That's called a contour map. Write it down. It's called a contour map. From the graph, we need to learn how to draw contour maps. And from contour maps, we need to understand how the object looks like. And those curves called level curves. Have you seen this before? Actually, the answer is yes. But have you seen this before? Do you recognize having level curves somewhere before? Contour maps.
Like a top view in engineering, like a top view, right view, front view, basically top view.
Oh, I did not know that, but I think I know what you mean. The top view in engineering, from left to right and so on. Exactly. Very good example. More examples. Where else did you see? Think. There's people over there. Yes? Yeah.
Like a graphical map.
Graphical maps. Yes, exactly. More? Maps, which we know from the... Let me show you. This. Look at that. We've seen this before. Many times in geography. Almost said geometry. In geography. We've seen this before. They're also called contour maps. They're used everywhere. So we will teach you how to use them in heat maps when the temperature is changing, in geography, and so on. So you see, you're looking from the top at those mountains, but somehow your brain knows more or less what it means, right? The smallest one is probably the top of the mountain. And if you want to hike from the valley, you have to go up over there, right? So your brain is not against this idea. Now we're actually going to classify it and learn it in a very strict way, so you finally know how this was all created. It was all created from calculus 3 ideas, multivariable calculus. Check it out. I have a really cool animation for that. I mean, look at this. This is exactly what level curves are. This is the bell. It's just upside down, right? From what we had before. Look at how amazing this is. At every level, it gives you a circle, but at some point, circle shrinks. So on the 2D, if you're a 2D creature that lives only on the floor, you only see changing circles. But from how they change, you can imagine what the 3D object is doing, right? The biggest application of that we are living in 3D world, and then from the changing level curves, we will be understanding what the 4D object looks like. That's the main idea here. Even though we cannot visualize 4D objects, we will understand how they look from the contour maps of a 3D object. That's, I think, the most phenomenal application. So, let's write down the definition. Basically, like so. This is a short definition. Level curves are curves of the form z equals some number. In the books, it's usually k. But it doesn't really matter, and people do not agree what kind of constant to use. Some number, 5, 17, minus 3. The level curves of the functions are the curves with equation f of xy equals k projected down on the xy plane. The graph of the level curves is called a contour map. Level curves. The bigger definition you have here, you don't have to write this down, but in general, level curves create contour maps. That's the idea. And the definition is f of x comma y equals some kind of number. Let's call it k, a constant. One more graph. You don't have to write this down, but this is the general definition from the book. You have 3D shape. You see people like bells a lot to show those things. At some kind of level, z equals k. It gives you a shape. That's maybe a lake. And that's how you know what's happening with the object at any level. So CAT scan of the brain usually does it in levels, and then it gives you those thousands of scans. Those are contour maps in a medicine. That's exactly how it's done. They collect them together, and it creates a nice visualization of the brain of the human, and so on. Look at that. So we will be talking about level curves a lot. It's like slicing the graph horizontally, and the contour map is like a bird eye view of the graph. So you see how cool is this? If it's complicated, what if it has like hills and downhills, pits in the 3D shape? That's basically mountains, right? There's some mountain and there is some lakes. In 2D, it will look like this. And we need to learn what does it mean. Is this the top of the mountain, or it's the bottom of the mountain with water there? So we need to learn how to do that. Usually they're color-coded. Heat maps are color-coded. Level curves, such as the one below, is used in maps to draw a 2D representation of mountains. This is a beautiful 3D animations I'm going to show you. Check it out. This is a heat maps. So this is a picture in 3D, but how does it look if you look at it from the bird eye? On 2D, it's full of level curves. Look at them at the bottom. Lots of circles. And when they shrink to smaller circles fast, that means there's a mountain or a pit happening fast. And by fast, I mean the tangent is steep. And if the level curves are far from each other, then it's a valley. It's just like going up slowly, and so on. And people usually color-coded. Blue ones is depth, red ones are heights. So that's how you know, usually from 2D, are we going up to the center of the circle or down? That is pretty cool visualization. So you see, the people usually color-coding these. I found lots of cool animations on this topic to show. I feel like many students are visual learners, so I try my best to use animations. Okay, those were deleted. That's sad. Okay, fine. Some of them get deleted. Look at that. Those are also level curves. When you slice, everything was smooth, and at some point, actually end up to have a circle. That means something is happening there. There's some kind of either pit or hill there. That is a pretty cool idea too. Okay, let's do some examples. Sketch the level curves. The same shape we had before. So your homework will have lots of level curves. It will challenge your imagination in a good way. You will feel your brain will be challenged. If you have some artistic part of your brain, that part will like it a lot. Because you need to have the 3D imagination, open your mind. Try to imagine how the teddy bear looks like if you slice it horizontally. So open, like think about that, okay? And that's exactly what we're asking you. It just looks like a boring homework, but it's exactly what it is, slicing and teddy bear, okay? So f equals square root of 9 minus x squared minus y squared. Sketch the level curves for z equals 0, 1, 2, and 3. How do we do that? Well, you just fix it as a number. This is how, oh, are you still writing? And tell me when you're done. So we already agreed that the shape was this drop. I imagine it's a water drop, but basically it's a mountain, hemisphere. But perfect hemisphere, what kind of mountain is that? I feel like it's a drop of water. That's nice to imagine that. Don't draw this picture yet. Let's learn how to write it down. Solution. This is how you're supposed to write it down. Solution. So z equals a square root of 9 minus x squared minus y squared. Level curves. Level curves. They ask us for specific one. As a scientist, you just do many. You do as many as possible, but we just ask you. You see, they don't ask you z equals minus 1, because that will be impossible. Z has to be positive or 0. They asked for z equals to 0, z equals to 1, z equals to 2. But as a scientist, you code it, and you ask computer to do like thousands of them, and it gives you a very nice list of graphs. Basically, it will be 0 equals, let me even move this, so you have like very nice vision, see? Z equals a square root, 0 equals 9 minus x squared minus y squared. Well, that means 0 equals square both sides, 9 minus x squared minus y squared. Well, that means the shape is x squared plus y squared equals to 9. Oh, that's a circle, radius 3. That's a circle, radius 3. And we can draw it. Circle, radius 3 into D. Here it is, we draw it. Good job. Good for us. We draw a circle. Centered 0, 0, radius 3. Now, guess what? We're going to repeat the whole idea. 1 equals a square root. From here, it will be 1 squared is 1 equals 9 minus x squared minus y squared. Equals, what kind of circle is that? Can you tell me? X squared plus y squared equals what? What did you say? 8. Agree? Let's just add up things. 8. Okay, so from 3, let's change the color. And I'll put it in the box, like so. Blue box. So in blue, I will have a circle radius 8. So much bigger. In green, we had the first one. No, it's not radius 8. Square root of 8. Thank you. And square root of 8 is what, approximately? It used to be 9, so it's 3. So it's a little bit bigger than, a little bit smaller than 3, right? So then I should actually shrink it. That was not smart that I made the first one so small. Z equals, let's do this way. Z was 0. That gives me the biggest green one. Duh, because it's at the very bottom. It was the biggest one. I just realized that. So that's the biggest. And now they will shrink. The blue one will be z equals 1. That gives you a smaller one. A little bit smaller. And you keep going. 2 equals blah, blah, blah. Simplify. Do you know the answer? X squared plus y squared equals to what? 5. Let's put it in pink. So square root of 5 will be the next one. that corresponds to the z equals 2. And the more you do, the better it gets, and so on. So I already know that the biggest choice will be z equals 3. It gives you the smallest point. We only have domain from 0 to 3. Like so. So what I'm doing here, I'm slicing from bottom to top. Z equals 0, z equals 1, z equals 2, z equals 3. Domain is only from 0 to 3. You don't have to have good numbers. You can have 1.7, you can have 2.3, and so on. So computer does it for you, usually. That's how the level curves look like. Now you see this picture. What if you only see level curves? They're color-coded, and you're like, I wonder if we're going up or we're going down. Well, z equals 0 was the first bottom slice, and it's the biggest one. Oh, so that's the floor. So the point in the middle is the top of the hill, so we're hiking up. That's how you do it. Make sense? The more z grows, the smaller the radius is. That's how I also can explain. What do you think about that? More. Let's do more. The great part about level curves is that they can give us a 2D representation of a 3D figure, which is especially important in higher dimensions. Not only that, we can also use level curves to sketch surfaces. Here it is. Let's sketch the surface x squared plus y squared equals z squared. I don't know how it looks. Unlike the previous example, z can also be negative here. So let's also sketch some negative level curves and see what's going on. And in general, you just do many. Z equals 3, z equals 2, z equals minus 2, z equals minus 3, z equals 0 is always pleasant to plug, and so on. And you start thinking about it as x squared plus y squared equals to what? Exactly. 9, 4, 4, 9, 0. So basically squaring whatever you choose for this graph. And now you know, okay, those are also circles. Those are also circles. They just have different radii every time. Radius every time. 9, 4, 4, 9, 0. Different circles. Now it goes up and down at the same time. So, but it's also kind of interesting when z is growing. Let's see. So the smallest one is 0, right? When we go from 0 to 2 and 3, the radius is 0, so it's a point. But then the radius is increasing. So now it seems like it's expanding up. Interesting. So it has points, circles, circles, circles. Now, when we have 0 and we're going down to minus 2 and minus 3, the radius is also increasing. Isn't it interesting? So yes, it's increasing down as well. Like this, like this, like this. So now it kind of gives you an idea of the shape. And the shape looks like this. See? Look how pretty it is. So oceans and mountains, or just 3D shapes. Because z was squared, no matter what z you put, and z is the height, the z would increase when you're squaring it and you increase the z. So even down below z equals 0, the radius is increasing. Is it too fast, or you're okay with that? Lots of graphs, lots of circles. And you see z is also always a slice of a teddy bear, okay? It's like seriously exactly what it is. Actually, I found the animation at some point, slices of a cat. I'm pretty sure it was not like physically done, but but it was very cool. Basically, cat scan of a cat. Duh. And that was pretty cool to explain too. Level curves. Do you have questions on any of this? I'm not done, but I just realized I should ask. Any questions of any of this? Questions, ideas, suggestions? Look at this. You will see lots of books have lots of good 3D animations. You guys are lucky. When I was learning this, there was no internet yet, and the computer still sucked a lot. So I did not know how it looks like. I only had to rely on my imagination. So like, this is probably how it looks like. Now you guys are lucky. Everything is coded for you. Some of them can be moved. In your homework, you will be moving them around and so on. You will see. So you see, everything can be moved and so on. So definitely visual learners are much happier nowadays. If you need to visualize it, they did it for you. See, it's all can be moved and it's pretty cool. Okay, more. So actually this is how it looks like. I just realized there was a picture. See, no circle at the 0, 0, circle radius 0. Radius is increasing when z is growing up. Radius is increasing when z is going down. Let's create this kind of cool shape. That's called, do you know the name of the shape? It's a cone. So ice cream cone is only positive part of the cone, but cone actually has positive and negative part. So if you don't look at the negative one, that's the ice cream cone. If you have ice cream on top of it, right? Now, after this, let me check this for a second. The homework will be asking you some questions about the domain, and you are very good in learning domains, right? You remember domains from all previous classes you ever taken in your life, right? So I thought maybe it's nice if I remind you the domain in, so limits are fine. You will do these just fine. Domains. So I just wanted to show you that.